All right, this video is on solving logistic equations. So we're going to say solving using logistic functions. We're going a little bit backwards here because we actually have already learned about logistic differential equations, and we're going to continue on making sure that we understand how those work. But we're actually going to look at how the logistic function is derived, so the actual function. We haven't really looked at that yet, but it does require separating fractions, so the fraction, partial fraction decomposition or whatever, which is why we haven't learned it before now, because you guys didn't know how to do that. So because I know logistic functions can be a little bit weird, you guys haven't worked with them a lot, we're just going to review a few things. So go ahead and write this down in your notes. It will probably make more sense now than it did the first time we looked at it. So we want to recall, this is review, that dp dt is k times p multiplied by 1 minus p over c. So we've dealt with this before. This is the differential equation. We know that k is the proportionality constant. And what I really mean by that is it's the relative growth rate. I know that c is the carrying capacity. And I know that the derivative dp dt really means it's the change in the population as time changes. So there were some things that we looked at. This is where we did some slope fields. So if you guys recall, we have our equilibrium solutions. And from here, those come from the factored form, and one equilibrium solution is from the factor in the front, the GCF, and that is P equals 0. And then the other equilibrium solution is when you hit that carrying capacity, so P equals C. And so our logistic function tends towards those two solutions. So when you look at your slope field, if you guys remember, those had horizontal asymptotes. They had derivatives of 0 right there. And so when we looked at this, we could see that C divided by 2, or half of the carrying capacity, was where the growth of this was the steepest. So if you guys remember what a logistic function looks like, it kind of goes like this, right? So this is where we have the steepest slope. And then the slope is a little bit less steep right here. And then the least steep is as you're getting close to those asymptotes. Looks like this. And then if you get above that horizontal asymptote, if your initial value is above that, then it's going to come down towards that carrying capacity. So one of the things, I'm going to go ahead and write in growing the fastest so I don't forget. One of the things that that showed up on our test that I think we maybe did not quite understand the notation of or kind of forgot about is how to find limits in regards to these things. So I'm saying the limit as time goes to infinity, and this x-axis down here is actually the t-axis, so this is representing our time. The y-axis is our population axis. So as time goes to infinity, what value is the derivative approaching? So as we follow this graph, as t goes to infinity, we're not asking like what's the y coordinate that we're approaching. I'm asking what is the derivative, and the derivative is the little pieces of slopes, right? The derivative is the instantaneous rate of change. So if you look as time goes on, the derivative is these slopes right here, your line is approaching that horizontal asymptote, so your derivative is getting closer and closer and closer to 0. As time continues, you're getting closer and closer to that carrying capacity, and your rate of change is nothing. You're just holding constant. So we're going to say our derivative here is 0. That's what we're going toward as time increases indefinitely. The limit as t goes to infinity of the function itself, so now we're saying what's the limit of the population itself? The limit there as t goes to infinity would be that carrying capacity. So that would be c. All right. So now we're going to go ahead and look at how we could solve the differential equation. And solving the differential equation is actually where the equation of a logistic function comes from. So I'm going to say solving the logistic differential equation. So to start with, we have dp dt equals k times p multiplied by 1 minus p over c. So when we solve logistic functions, logistic differential equations, the first thing we want to do is we want to separate the variables. I want to get all of the p's over here, and I want to get all of the t's over here. And there's no t in the problem, as you can see, so we're just going to leave some coefficients over here. We're going to leave some numbers there to work with, but the p's we're going to want to move over. And this problem is going to be a little bit easier for us to deal with if we do not have this part right here as a fraction. And so what I'm going to do is I'm going to multiply the inside of the parenthesis by c. So I'm going to say c multiplied by 1 is c, c multiplied by p over c is p. And since I'm multiplying this part of the right side by c, then to undo that I have to divide this part by c. So I'm going to say this is k times p divided by c. Okay, so I want all the p's to be over on the side with the p's. So I'm going to go ahead and say I'm taking this part right here and I'm going to divide it over to the other side. So that gives me 1 over p times c minus p. dp equals k over c dt. All right, now the k can stay with the dt. I'm okay with that, but the c is the carrying capacity. I'm actually going to move that over as well. And for me to move that over, I have to multiply it over. So I multiply it over, that gives me c over p times c minus p dp equals k dt. So this is the point where we have completely separated our variables. All our p's are over here. I've got a number, like a coefficient, and then dt. So I can go ahead and say, yep, I'm ready to integrate these now. Now this side is pretty easy to integrate. I'm just going to have kt, so that's pretty easy. Over here, I have to think about, it looks like I've got like the product rule on the bottom, and I have to think about, this is my variable, right? The p is my variable, so I'd have to say I got to figure out what my u is and what my du is, and this part right here is actually the part where we have to decompose the fraction. So I'm going to go ahead and do the work for that. I'm going to say that c over p times c minus p is a over p plus b over c minus p. So there's my fraction. I got to break it apart so that I can integrate it. And just keep in mind that p is your variable. That's what you're plugging a number in for. So I'm going to say c equals a times c minus p plus b times p. So first I'm going to go ahead and say I'm just going to plug in 0 for p. So that's going to give me c equals a times c plus b times 0. So that's nothing. So I have a times c, and there's a c over here. So if I take the a times c and I divide the c over, then that means that a must have a coefficient of 1. Or not a coefficient, a must equal 1. Sorry. So this is zeroed out. I've got a times c equals c. I divide c over, I get a equals 1. Next, I'll go ahead and use p equals c to plug in. So that gives me c equals a times 0, c minus c is 0, plus b times, plug c in for p, b times c. So that's not there, and this time I've got b times c equals c, and I can divide by c on each side, and I find that b equals 1. Okay, so let's look at what we have now. This means that instead of integrating this and having it equal the integration of that, I can now say that what I'm integrating is 1 over p dp plus 1 over c minus p. Yep, was that? Yep, that's how I separated them. So 1 over p plus 1 over c minus p dp. And that equals k dt. Whew. Okay, let's keep going. So when I integrate this, I end up with ln p plus. When I do this one, I have to be careful because this is actually a u substitution problem because the variable is negative. The variable has a derivative for that reason. So I know that my u is c minus p. My du is negative dp. So I'm actually integrating negative 1 over u. And this other side is kt plus c. Okay, so now I have ln of p minus ln of c minus p equals kt plus c. Now, if you guys recall, I've been using the property of logarithms to take two different logarithms and put them together. So the way that this would be written right now is I would have ln, I'm going to write this off to the side, you can write it or not write it, it's up to you, of p divided by c minus p. And eventually I want to have an equation that says p equals. So me having fractions p over c minus p, that's going to be hard to solve for p there because the denominator has a minus in it. I would much prefer to have a fraction where it is c minus p over p like that. That fraction is easier to deal with because I can split it apart. So what I'm going to do is I'm going to take this entire equation and I'm going to multiply it by a negative 1. So now that I did that, I've got negative ln p plus ln of c minus p equals negative kt plus c. And I still have plus c because if I distribute a negative to a constant, it's still a constant. So now when I write this as an ln, and I kind of combine these things, it's going to be this one minus that one. And so now when I write it as division, the c minus p gets to go on top. And that makes my life a little bit easier. All right, so now we've got to solve for p, so I'm going to go ahead and do e on each side. So I have c minus p over p equals e to the negative kt plus c. So if you guys remember, this side right here is really e to the negative kt times e to the c. And e raised to a power of a constant still represents a constant all on its own. That's still a constant. So now what I have on this side is a constant, but I can't use c. Let's go back and fix this. We can't use c because we were already using c as the carrying capacity. And that was me just really not paying attention. So we're going to go ahead and use the letter A for our constant because that's a letter that we have not used yet. Okay. Sorry about that. Forgot that we had C for our carrying capacity. All right, so E raised to a constant is still a constant. So that's going to be the constant times E to the negative KT. And that equals C minus P over P. All right, now on this side, I can go ahead and split this fraction apart. So that's what I'm going to do. I'm going to say this is c over p minus 1. I'll go ahead and add 1 to the other side. So I've got c over p equals, I'm going to put the 1 first because that's how the equation that we're coming up with right now is typically seen. Typically has the 1 in the front. And then I'm trying to isolate the p value. So if you guys remember, whenever we have a fraction equals something like that, you can take this part and the p on the bottom and you can actually switch places with them. So I'm going to say c over 1 plus a e to the negative kt equals the population. And this right here is the function that we use for logistic equations. This is the logistic function, and that's where it comes from. To be able to use the logistic function, our variables, remember, are p and t. That's kind of like our x and our y. So the numbers that we need here is we need to solve for a and k. So c is that carrying capacity. They're typically going to mention that in the problem. But a and k, those are two values that we're going to have to get from points that we plug in. So it's going to be like they give us an initial value, we can plug that in and solve for a. They give us another value, we plug that in with the a that we just found. It helps us find k. So those are some things that we have to do before we can use that function and work with it.